into it. All right. So Amazon transaction processing. The topics we're going to cover, transaction scale, right? Basically big, how big Amazon is, that sort of thing. Transaction process and principles, we'll get in a big chunk of that. And then on Thursday, we'll start talking about the centerpiece of the lecture, which is this two-phase transaction model, two-phase commit. And then we'll have some secondary topics for network architecture and object description languages that support these sort of operations. So we'll get to it all. But where we're starting is with Amazon. So Amazon was launched in 1994. And in 1994, the internet wasn't something that everybody had in their house or on their phone. It was still a fairly specialized tool that not a lot of ordinary people had. For example, I didn't have internet in 1994. I think I joined AOL, if I remember, probably in 1995. So I was a little late to the party there. But yeah, 1994, not a lot of people had it. Anyway, Amazon at that time was launched as an online bookseller, primarily to deal with some of the inventory challenges that physical bookstores had. And we'll talk more about that as we get into all this. So Amazon was kind of in that sweet spot in history, right? Because you want to be there before online businesses are set up, and then you got to try to catch up with everybody else. But if you start too early, you're not going to make money. Maybe you're going to burn through whatever funding you have, right? Because it's 1994. And these guys aren't rich yet, right? So they got to kind of be in that sweet spot and do a really good job and just plain be lucky. So for sure, some organization would have come along if Amazon hadn't been there. Some organization would have filled that spot to become, the world's premier retailer. But as it happened, Amazon was the one that did it. And as it grew, it had a stretch early on where it was basically doubling every month, right? It was doubling in terms of everything it was doing. And that is pretty insane. Does anybody know what doubling 12 times over the course of a year is an effective multiplier for what you're doing? Or another way I'm asking, what's 2 to the 12th? 2 to the 12th power. A lot, yeah, I'll accept that, but a more precise number. It's 4,096, right? The easy one to remember is 2 to the 10th is 1,024, but 2 to the 12th is doubled twice more to about 4,000. So that basically means whatever Amazon was doing, in month one, they needed to do that 4,000 times by the end of the year. So if it was enough, if they could have one guy keep up with their business in month one, they needed 4,000 guys to handle it, right? If they had, one server to manage all their traffic at the start of the year, they needed 4,000 servers by the end of the year. It was crazy. So anyway, obviously it had a lot of scale problems. So things like order fulfillment, right? Taking the orders through the website, getting people to contact the publisher, filling up the boxes, and the start, you might go from some sort of voice system, right? If the orders are just trickling in, you can have one guy who actually, calls up the publisher and says, hey, these are the books I need this week. But, a few months into that, you can't do that on voice. You got to set up some automated process where you're sending them all that data. Same thing for website traffic, right? Your website, maybe it's you got one server helping out with that, but if you're multiplying that traffic by 4,000 times, that's a much bigger problem. Transaction processing, right? You can have some kind of slow pokey system if you're running basically 1 or 2 transactions per minute. But if that's multiplied by 4,000, boom, suddenly you got a whole different problem, right? And inventory management. Again, you got to have trucks coming in, bringing the books. You got to have guys tracking how many books there's supposed to be. Somebody put them in boxes, slap the shipping labels on them, all that stuff, just the space needed for the facility. If you're processing 4,000 times as much stuff, it's a huge change, okay? So lots of scalability issues there from Amazon's, basically from when they first started. Another issue, early on, first 10 years, Amazon was focusing mostly on retail. And retail was kind of easy, the stuff they were targeting. So initially, it's books, right? Amazon then wanted to branch out into other things that were like books. So what are like books? DVDs, CDs, VHS tapes, any of that kind of stuff. A book, you put it in a box, put a label on it, and ship it, right? Same thing. These other things, they're commoditized goods. You put them in a box, you put a label on it, you ship it. The handling is basically going to be the same. okay? But these other things that are digital goods, they are much different, right? So music downloads, for example, you have to set up some sort of high capacity system that can handle all of these downloads that people want to do. And importantly, handle many, many simultaneous parallel downloads. So it can't be just one user connects to the system, downloads a file. When he's done, the next user can get their file, right? Has to be a lot of stuff being able to work at the same time. Likewise for Kindle, right? So these days, people are probably writing books all in digital format, right? And so it's pretty easy to make a Kindle version of that. You just, take the text from the Word file or whatever software you use, convert that to Kindle format. But, 20, 25 years ago, most of the books were just on paper. So they had to have some kind of system set up. People were scanning these books and getting the text, and you had to allot resources for that. And of course, Amazon Video, right? Basically being a competitor to Netflix, that's a totally different business from shipping books. So Amazon branches off into these digital things, a lot of stuff's going to change. Now, as Amazon got really, 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 really big, one of the problems it encountered fairly early on is that there was nobody out there that could build these systems for Amazon or build them affordably. So, for example, if you're a typical small business, right? Pass notes if you got to talk or text or something, but I hear this low rumble of chatter in the background. Anyway, if Amazon is growing really big, if they're a small business, right, comparable to what's already out there, then yeah, they can call up Cisco and say, hey, Cisco, set up a network for me. And Cisco will say, okay, this is what our other businesses are using. You get something like this, and that's fine. Or if they need a database system, right, they can call up Oracle, and Oracle will say, yep, okay, you want one of our small to medium business plans? Great, we'll set that up for you. But Amazon got so big so fast and was trying to branch out into all these other things, there was nobody out there that had ever needed a system like this before. So yeah, they could have paid somebody on the outside to build it for them, but A, that's going to cost a bunch of money. B, the people on the outside might not have any more experience doing this than Amazon does. And third, what happens if they contract with somebody to do the work, and then midway through the project they say, no, you know what, this isn't quite going like we thought it would, we're done, These are all tremendous risks for Amazon. So Amazon said, you know what, we're going to design all these systems ourselves, we're going to build them in-house, maintain control over the project, hopefully keep costs down more, and guarantee that we're going to end up with something useful. Maybe it's not a perfect system out of the gate, but we're going to end up with something useful, not some half-finished train wreck. And all of that stuff that they built, the main concern was scalability, because if they're going to keep growing and succeeding in the internet, right, internet retailing, they need to maintain performance no matter how big the operation gets. Now, one popular misconception is that Amazon's is the origin of Amazon's cloud service. So a lot of people have this common sense kind of idea that, Amazon needed a bunch of hardware for when its site is busy during the day, right? Regular shopping hours, sure, it's going to be busy. But overnight, suddenly they have all of this idle hardware. But that's actually not true. In fact, Amazon was barely keeping up with demand all through those early years. What was happening in the overnight is they were doing routine maintenance type issues, right? So like installing updates, installing patches, doing database cross checks to make sure whatever's in one replica matches what's in another replica. Stuff like that needs to happen. And even the machines periodically need some time off too. So all of that kind of stuff was what they were doing in the off hours. Cloud services for Amazon had a different origin that we will eventually talk more about. Okay. These days, right, Amazon is this massive hybrid cloud services business. Most of its revenues still coming from retail. Cloud is about 13% of its business. And we're going to discuss Amazon's transaction processing system in the context of just the stuff Amazon sells. But really, it's only a fraction of their entire operation most of the time, right? Amazon sells a lot of cloud services to other businesses, and they're very often running transactions for them as well. Amazon maintains its competitive advantage by continuously innovating and building on its existing operations. So for example, they started out early just selling books. Once they got really good at order fulfillment for books, it was not a big stretch to go into other similar goods like DVDs, CDs, VHS tapes, stuff like that. Likewise, all of the technology that it needed to manage scale, basically having standardized interfaces and not constantly designing new ones, that was the basis of its cloud system. Basically, vendors were coming to Amazon, selling stuff, and they had to upload a certain amount of data in order to do that. So things like product descriptions, images, stuff like that. And at some point, Amazon figured out, you know what? We're taking the vendor data, but it doesn't specifically have to be data from a vendor. It could be from anybody. And it doesn't specifically have to be product data. It could be any type of data. And we could manage that and we could sell it as a business. There were a lot of businesses out there at the end of the aughts that were experiencing a lot of trouble managing their growing piles of data. Anyway, if you're interested in what Amazon has up its sleeve, perhaps, little article about 12 industries Amazon could disrupt next. I know not all the links in the lecture slides are super current, but this one I just grabbed over the weekend, so it's pretty recent, and I don't know, maybe worth a read if you're interested in this. Ow, shit, my shoulder just felt like I got stabbed. Anyway, I don't know. You get old, things start to hurt. Okay. Anyway, so yeah, that's current and maybe interesting. I don't know. You can decide whether it's interesting. So here's Amazon's business. They break it up into different threads, like what its revenues are from. So, example, this top line is online stores. The second line, third-party sellers. The blue line in the middle, AWS. That's cloud, Amazon Web Services. If you look over here, this chart in the upper right, this kind of gold one, you can see it's had pretty exponential growth the last few years. So in just 6 years or so, it's almost multiplied by 10. In not much more than 2 years, it's doubled. So it's still growing super fast. Even their regular retailing had this huge burst of bonus revenues because of COVID when people couldn't get out much, So this 280 billion, that was a big jump, but 280, again, almost doubled in a couple years to 470 billion. So it's still getting really big. I feel like next year's revenues are going to taper off with the growth somewhat, but I guess we'll see. We shall see. Anyway, Amazon is big, really big. You all know this. Last year's revenues, almost 470 billion. Depending on the measurement you use for e-commerce, I saw numbers when I was looking up this factoid, anywhere up to like 56, 57%. But it really depends on what you categorize and exclude in the realm of e-commerce. So I went with the lower numbers, which I figure are probably a broader perspective, and those ones gave about 40%. But again, this is just one of those factoids, and depending on what you define as e-commerce, could be higher or not. And it also has the world's largest public cloud service. So because Amazon is super big, there's going to be massive amounts of computations, massive amounts of network traffic, massive numbers of database operations, right? Basically all day, every day. So for example, on Prime Day, Amazon has to process hundreds of transactions per second. And you might be thinking, well, that's not such a big deal, right? How much can a transaction be? I just, make some call to some database, get some number back, boom, it's done. Well, the problem with transactions per second that high, number one, a lot of those transactions are going to interact with similar data, right? The other thing is that to a point, they all kind of have to happen sequentially, right? Because if you don't do parts of them sequentially, what can happen is just like the ATM problem we saw, right? You could have multiple transactions get registered as happening. People get their stuff, but Amazon only tracks, the final result. So, and transactions per second also, they're involved with a bunch of different databases, not all of them within Amazon. So Amazon has to contact credit card people, may have to arrange for shipping. There's a bunch of stuff with a bunch of different systems involved in processing any one of those transactions. Anyway, we can pull up some factoids here though, which I'll do. So just a couple of them, so, because factoids are always fun. So for example, for Prime Day, the Amazon team added 152 petabytes of storage. Think about that, 152 petabytes, that's a lot. It really is a lot. And think about this in terms of space, right? If you have ever copy a few gigs of data to or from a USB drive, that takes a while, right? Especially if it's a lot of small files, that takes a while. So think about it, when Amazon's doing 152 petabytes, which is 152 million gigabytes, you know for sure that's not going to be just on one machine, right? That's going to be on a whole bunch of different machines working in parallel, because there's no way you're going to transfer that much data that fast on, one connection. All right, so, and another thing, during Prime Day, Amazon's Simple Queue service set a new traffic record by processing 70.5 million messages per second. Okay, again, there's no way you're doing that on anything like one machine, right? You have to have a whole bunch of different machines working in parallel so that each one takes a tiny slice of the traffic and can process it at that speed. All right, so that's some stuff. Here's another one. There was something with trillions. I missed that one. Do you see the trillions? Well. Oh yeah, well, trillions of calls. Well, whatever, that's fine. I saw it earlier. But these are just factoids, just to give you an idea. Amazon's super big. You can't possibly do this on one machine. You have to set up a lot of stuff happening in parallel. Okay, which is going to be important. That's something we'll come back to. Okay. Now, on top of that, peak transaction is typically a lot higher than the daily average. For example, during the regular course of retailing, Amazon's typical transaction rate is maybe about 60 per second, which is still a lot, right? But compare that to several hundred on Prime Day, right? 10 times higher. And even within a day, there's daily cycles, right? There's going to be busy parts of the day, quiet day. So like 8 p.m. in the early evening, people do a lot of their shopping. Very quiet at 4 a.m. So there's some kind of multiplier, even for the 600 transactions per second. Even that has a multiplier for busy parts of the day. Now, again, transactions isn't just some simple operation in RAM. There's a bunch of extra work that has to go around it, right? So there's the transaction itself, sure, but there's also all kinds of supporting information. When Amazon, for example, sends you the web page indicating that the transaction is complete, they typically include a lot of stuff in it. There's graphics, there's other details. There's also a lot of browsing activity around each transaction, because most people that look at most items don't buy them, right? Typically, we look at a lot of different items before we actually pick one to buy. And then there's a whole bunch of different database operations, what I call secondary transactions, for other systems like inventory tracking, for analytics, all the stuff that Amazon tracks, those systems have to get updated too. The key takeaway from all this, if you're going to be a big retailer and manage this kind of scale, you have to have some kind of massive, reliable, high-capacity cloud service. If you're big enough like Amazon, you can deploy it yourself, right? You can build your own. If you're not as big as Amazon and IT really isn't core to your business, you're going to rent that kind of system from somebody else, right? But for sure, you need to have it. Otherwise, it's pretty hopeless. Okay, so what are transactions? Well, there's two different definitions for them. One is the ordinary, ordinary person on the street view. And that is simply that transactions are any sort of exchange involving a payment, right? It could be I buy something from a store, I give the store money, they give me the goods, or it could be clearing a debt, right? You log into your online banking account, you pay off your credit card bill. That, would be a kind of transaction. The database view is a little different. It's an action that is a single logical unit, but could potentially encompass multiple operations. So for example, suppose you create a new customer account. That is definitely going to be a single logical operation. But again, there can be multiple database operations, right? There could be stuff for creating your profile in one table. There could be another factor that's setting up your password. There could be another thing for setting up any security features that are needed internally for your account, and replications of all of the above, right, to different storage places. So all of those things, right, creating a new customer account, part of one logical unit, but again, potentially quite a few database actions. Likewise, a single update to a database, that could affect multiple rows or maybe just one field in one row, whatever, that could be it, right? So for example, suppose you have a list of customers and the zip codes change, right? So you have to go through and verify, oh, here are all these address changes we're processing through for this whole list of customers. Again, single logical unit, right? Processing a single update, but it could affect multiple records. Or simply processing a query, right? Processing a query that might involve multiple tables, might involve breaking up those tables into smaller slices so you can run it faster in parallel, whatever, okay? So a transaction, single logical unit, but could entail, more complex operations at the database level. Okay. And I hope most of the time it'll be pretty obvious which one we're talking about. I mean, if you're reading something like in the Amazon details where it says they're processing, 1 trillion transactions over the course of the day, they don't mean 1 trillion people buying stuff, right? Because that would be insane. That would be like everyone on Earth buying 100 different separate things from Amazon. Yeah, that's not going to happen, right? So if you see some crazy number like that, that means how many database operations they processed. Anyway, okay. Now transactions are going to follow some kind of request and agreement sequence. Basically, the user is going to ask to do something. The system is going to check and see if it's feasible. And if it is feasible, then they'll approve it. You can go on to the next step, right? So for example, you go to Amazon, you try to add a product to your cart, right? Now, most of the time that's not a problem, but it could be that it's, a one-of-a-kind item that's already, that only exists once. There's no replacement for it. And once it's sold, it's gone. And it could be that, a microsecond before you click it, right, somebody else has already bought it. And there's not time to update the site before, you click on it. So that might be refused, right? Amazon might say, oh, sorry, this item is no longer available. And you'd be like, but that part of it won't go forward. So anyway, you try to do something, you try to add a product to your cart, the business agrees to it or doesn't. Eventually, you get to the checkout stage, assuming you add something to your cart, you get to the checkout stage and either the transaction successfully gets processed or it fails for some reason, right? So it might be you want to buy this stuff, you put in your credit card number, you type it in wrong, you realize, oh wait, that's the wrong credit card number. It's expired. I don't, have another one in the system. I don't have my wallet handy. What do? I'm going to cancel this transaction. I'll come back later, right? Or you could try to do the transaction, type in your credit card number, and then Amazon sends it out, and they say, oh, sorry, you don't have enough space left in your account, enough remaining credit to actually buy all this stuff. So sorry, try again later, right? Anyway, you try to do stuff and the system approves it or doesn't. And very often these request agreement cycles are going to happen with other organizations. For example, Amazon isn't keeping all of your credit card account information under its roof, right? That would be illegal. They have to go through the credit card companies to do that. If it's a vendor selling through Amazon, you contact Amazon to buy some stuff, Amazon's going to have to contact that vendor and arrange for shipping perhaps, okay? So it can involve outside systems as well. But in any well-designed system, the final permanent changes from the data don't happen until everybody involved has agreed that the transaction is going to happen. So you make sure everything's good first, and then once you're verified that it's good, then you make the changes permanent. And this prevents basically a lot of corrective work and a lot of over-checking. So I give an example. Suppose you have, you're in a two-person team for some group project in some course here, okay? And the person you're working with is kind of a fuck-up, right? All they do, they send you chunks of plagiarized text that they don't even bother changing the color of the text block that they copied, so it's kind of obvious. I actually had a student do that once, anyway, many years ago. So yeah, you got to check for that. And maybe they're terrible with the spelling and they don't use spell check, or when they do use spell check, half the time they pick the wrong word. And that's the stuff that spell check isn't going to catch. And so you really have to go through it with a fine-tooth comb to make sure everything's okay, right? That's the sort of problem that would happen if you didn't check that the database, that everybody was ready to make the transaction. You'd have to be a lot more careful processing it. You'd have to be, allot some resources to going back and rechecking that everything was correct afterward. On the other hand, if your teammate is good, and you say, yeah, I don't have to worry about this person, right? You get the data from them, you make a quick scan through it just to see that there's no kind of crazy formatting issue, right? Like maybe some of the page didn't print correctly or something, but you know the data is going to be good, right? You're confident about that. So the checking that's required is going to be a lot less. Have you guys heard the joke about, no, you haven't. Okay. You know, when you get old and you finally die, you should look up all of your former group project members and have them carry your casket and put it in the ground, right? So they can let you down one last time. Yeah. Anyway, been there, done that. Okay. So talk about the transaction process. So the front end, the stuff that the customers actually see, right? Hopefully you've all ordered something from Amazon or some other online site. I mean, I'm guessing you're here, so if nothing else, you've probably at least paid your tuition bill online. Anyway, basic process, right? You log into the site, you browse around for a while, you add some items to your cart. Eventually you begin the checkout process, you pick your delivery option, and you pay. Boom, right? That's how that works. But the back end is a little bit more complicated, right? There's a whole bunch of different things that Amazon has to manage. So Amazon has a whole bunch of different systems that are all working together to process all the data needed that Amazon wants to track. Some of those are internal, some of them are external, like business partners, vendors selling through Amazon, maybe shipping services like FedEx or UPS, maybe credit card companies, whatever. And there's also going to be, you know, basically a cascade of database activity. There's a bunch of different databases that every time you do some kind of update in the system, they have to be updated to reflect that. So things that happen with the transactions, stuff like inventory checks, right? Do we have this actual thing in inventory? If we have it, where are we storing it? You have to put a hold on it, right? If somebody adds something to their cart, you want to make sure that nobody else can come along and buy it. So your database has to be updated. Say, oh, this item is in somebody's cart. Can't sell it right now. When something finally gets purchased, right, you're going to update that inventory levels. You say, nope, it's not in the warehouse anymore. Now it's on a truck. Maybe the fact that the inventory in the warehouse has gone down enough is going to trigger some reorder point where you bring in a new shipment. Okay, credit card validation, payment processing, obviously that has to happen. Supply chain coordination, right? So when the call goes down to the warehouse saying, you know, somebody is buying a new bowling ball, somebody has to pull it out of a bin, you know, put on roller skates, go to the other side of the warehouse, drop it in another bin to get loaded onto a truck. Somebody has to figure out which truck it's supposed to go on. Database has to get updated when that happens. Say, yep, this package is now on this truck, and some system has to do some math to figure out how long it's going to take, when the approximate delivery time is, as best as Amazon can guess. So a whole bunch of supply chain issues have to happen. And of course, the website itself has to be updated, right? If there were 5 of those bowling balls in inventory, boom, now there's 4. And that has to be echoed to everybody who might be looking at those web pages, or at the very least, has to be updated in the database. So if somebody comes along and looks at that page, they see the right number. Okay, so a bunch of back end stuff kind of happens. Now, I don't expect people to memorize all these things. This is just kind of big picture stuff of what's going on behind the scenes. Okay, now talking more about the back end process. Of course, anytime you add something to your cart, the relevant item in the database is probably going to be locked and be unavailable to other users. And the lock will eventually be cleared one of 2 ways. Either the item gets bought, in which case the item isn't in the database anymore, right? It gets, oh yeah, you sold that one. Or the process gets canceled and eventually its residency in your basket times out. So depending on how that happens, right? So if the user deliberately cancels the process and says, nope, empty my cart, throw this stuff away, fine. Amazon's going to remove the hold on that item, right? But if you try to check out and the checkout doesn't go through, unless you deliberately remove those items from your cart, they're going to be there sitting in your cart for a while. Now, it will eventually time out. We'll talk about that in a little bit. But, you know, how long it stays in your cart kind of depends on other factors. Anyway, if the order does go through, right, of course, what's going to happen? The warehouse is going to receive that order request. It's going to make arrangements for delivery. Inventory levels are going to get updated. All those kind of things are going to happen to make sure that all of your databases reflect that the transaction was ultimately completed. That's the big thing, is at the end of the day, either the transaction was finished successfully, great, all the databases should reflect that, or the transaction failed, and again, all the databases should reflect that, okay? One way or the other. You shouldn't have some databases thinking that the transaction was successful and others thinking that it failed, because then clearly there's going to be some kind of conflict there. Okay, now some pitfalls, some things that can go wrong. Obviously, it's sensible to maintain the sequence of data updates, right? So every step in the process happens in a unit and either succeeds and enables the next step, or fails and you could try it again, or potentially aborts the whole process, right? So, for example, I mean, success isn't very interesting to talk about, right? The transaction goes through, great, that's fine. But there's different ways that failure could happen. Suppose your transaction fails because you enter in a wrong credit card number, right? Obviously, Amazon's going to try that again. If your credit card gets called because of some kind of fraud alert, well, Amazon's going to respond differently to that, right? They're going to say, oh, sorry, there was a serious problem. Who knows? Maybe Amazon is going to report you to the police, and they have a different process for that. But I don't know. If you then try to use a legit credit card, will Amazon accept that? Yeah, probably. They still want to sell stuff. Or, right, suppose there's some hardware failure in the system. Suppose you're trying to buy something, and then at some point, you know, so either maybe your router catches fire, and there's nothing Amazon can do about that, or whatever piece of hardware that Amazon is using, maybe that suddenly becomes inoperable and you get booted from Amazon, you lose your connection, you know, that transaction fails. And in that case, yeah, the whole transaction would obviously get canceled, right? Suppose there's some freak event where even though Amazon might maintain backup copies of whatever application you're using, maybe both of the ones immediately available to you go down at the same time, and Amazon can't do anything about that. Anyway, if you don't follow that, strict sequencing of data updates, you could have a whole bunch of obvious problems, right? So example, the inventory could get updated before the credit card gets validated, in which case, hey, maybe something goes wrong with the credit card, and so they gotta, you know, go back and fix inventory. Or you could have some supply chain update happens like, oh, we think it's on the truck, right? But you haven't actually paid for it yet. So this is why you need to have all those things happen in the proper sequence so that you feel confident about going to the next step. If you don't, right, then again, like the example with the bad group member, you have to exert a lot more care in reviewing everything that goes through, because you're going to have to go back and look at things and make sure that everything is okay. And the occasions where something goes wrong, you're going to have to dig back in and fix them. Okay. Now, simultaneous access. So we talked about simultaneous access in the context of isolation, right? When we were talking about ACID properties, isolation is good. In principle, it's bad to allow multiple users simultaneous access to the same data, right? Because what can happen? Just like the ATM example that I gave, you could have interleaving of database operations. For example, remember the ATM example? Two people both withdraw $500 from the account, but because the operations aren't isolated from each other, the bank side of things only recognized that $500 was taken out, right? Only that it was taken out once, not that it was taken out twice. So when that happens, you can also get things like dirty reads. For when databases store data from transactions in progress. So imagine if there are multiple replicas of the data and there's a transaction in progress, right? And it's updated one, but maybe hasn't updated the other two yet. If you look at either of the other two, you're going to get the wrong answer, right? Because the transaction is done. So if you don't have isolation on your transaction and you don't make sure that all the replicas are updated before someone can look at them, again, you could have database conflicts that way. You could get the wrong answer when you ask the database a question. Now, the problem is, remember about ACID properties, scale, right? They don't scale well. In particular for Amazon, if they're getting several hundred transactions per second, in very, very, very many cases, those database operations are going to overlap, right? Imagine if you have these massive tables of data, and anytime somebody does a query on them, right, what's going to happen? That table is going to be temporarily locked to everything on the outside while that query is running. So nobody can make an update to any of those, which means You know, nobody can go in, maybe nobody can make a review, maybe no transactions can happen to update the quantity available. Who knows, right? There's all, depending on how their database is structured. In fact, but basically anything Amazon would want to do to change that can't happen. Even if Amazon is like updating their system to add new products, which they're doing fairly often, right? What's going to happen? Nobody can run a query on that database until that process is done. So if you have very big tables, and especially queries that involve multiple large tables, yeah, that's going to be a big headache, right? A lot of these database operations are going to overlap, and you have to find some way to deal with that. So 3 basic options. Number 1, you could throttle the transaction rate, right? You could basically say, nope, people got to wait, right? Whatever you want to do, people got to wait. But aren't going to like that, right? Because it's going to make the system really slow. Users inside Amazon are going to hate it because it's going to take them longer to do anything they need to do. The customers are going to hate it because it's going to take them longer to shop. Eventually, they'll all go to Target or Walmart.com, whatever. Maybe find the same stuff on eBay. I don't know. Okay, so Amazon really doesn't want to throttle the transaction rate. That is absolute last resort. Second, this is what a lot of the big operations do. They group the data in much smaller, more isolated sets, right? So I'll draw a picture because I talked about this earlier today, but I feel like a picture is warranted. Oh no, I can, good. Okay, imagine you have massive database table, right? So big table. And somebody runs a query on that, right? And nothing else can happen with the table while that query is running. Otherwise, you might get conflicting data, right? If you update it, you have to update every replica of that table, and nobody can run a query on until all those updates are done, right? So it's going to be slow. But what if you break that table into a bunch of slices? So I'm going to lift a few of these. We're going to make copies. You have a bunch of different copies, right? You put it into slices, and then at that point, what happens? Well, the queries that you're doing on this big table, they're not going to take that long, right? They're going to happen much, much faster because they're happening in parallel. You might even be able to say that a query only affects a tiny part of the table, right? There's only a tiny part of the table where the data you're looking for could be. And in that case, the operation is going to happen much faster. And if the operation happens much faster, you can support a higher transaction rate on it, right? You can process more operations with that tiny slice of the database much faster. And Amazon uses this, Google uses this, I'm sure Facebook does, although, you know, it hasn't really been something they've harped on. But, you know, for example, for Google, this is super important. Google has literally trillions of web page trillions of records of web page data that it has stored. If it had to do an update and lock that table, you know, before anybody could do a query, that would be a total train wreck, right? So they split their massive web page database into slices like this, and updates happen only on the tiny slices. All right. I lost my thing. Okay. Well, what? Yeah. So yeah, to a point, businesses do this, number 2, right? But even that isn't going to necessarily solve all your problems. Sometimes businesses do need to allow some data access. Let me give an example. Well, you know what? I'm going to actually just give an example to start with. So imagine if you went to Amazon.com and you wanted to look at a product, and Amazon says, oh, well, on our pages, we keep the quantity available, and somebody else is looking at that product right now and might press a button that could change that, so we actually can't let you look at that page, right? So when you went to Amazon and you looked at the product page, if somebody else was looking at that product, you'd get a little message saying, please be patient, someone else is looking at that product right now, you can look when they're done. What do you think the customer reaction to that would be? Would they be happy? They would not be happy, right? They would go somewhere else. Yeah. So again, that's the kind of simultaneous data access. Amazon's kind of got to allow that, right? It's a retail site. Amazon, obviously, it's a good idea to put in, you know, the number of how many things are left because people like to know that. But if you say, yeah, you can't, all access the same page at the same time, that clearly people are going to react negatively. So, for example, what happens if multiple users simultaneously try to buy the same last item? Well, one of them is going to be disappointed, right? If it's a unique, one-of-a-kind item, there's only one in inventory, there's no way for Amazon to split it into two more. Yeah, that's just it, right? That's it. So, yeah, there can be only one. But a bigger one, what happens if two people try to use the same gift card? Well, if Amazon's not careful about that, they could end up in a similar problem to the ATM machine example, right? They could have two people try to use the same gift card. They both do it at the same time. But then what happens? Well, they use it twice. Hopefully Amazon figures it out before the goods actually get delivered. But then it definitely means Amazon's going to have to maintain a lot more care to checking this gift card usage, right? So the solution to that is locking, right? So locking in general, when one user is using a particular thing, it gets locked so other users can't use it. And that can be applicable to data rows, right? So if you have a particular record of something, for example, anything you put into your cart, that could be done. It could be a lock on a particular field in a table, right? If you're doing some format update in a table, you might say, yeah, well, this change is pending. Nothing else can go in and edit that data. But, locking is understandable as a general concept, but it still entails some further questions. So number one, how long should a lock last? So if it's like some product that you have a lot of in inventory and somebody's only trying to buy one and you don't normally sell that many in a given week, yeah, it's okay to leave that lock on for a while, right? Probably not going to cost Amazon anything. But if it's like the day before Christmas and Amazon somehow has a stash of this very hot item and somebody has added, 100 of, whatever the new thing is, like 2022's Furbies or something, they add 100 of those to their cart, Amazon's not going to let that lock sit all day, right? If somebody goes away, Amazon's going to say, oh, nope, you quit. We know we're going to sell these today. We know it's going to be harder to sell them tomorrow. Yeah, we're going to end that lock. So they use some, some kind of dynamic knowledge to determine how long a lock can last. They might even say that the thing is still in your cart, but they unlock it for other users so that if you actually go try to buy it, you might get a note saying, oh, sorry, this shipping on this is delayed. So even if it looks like there's not a lock, there is a lock, there might not be one. The other thing, how many things can a single user lock? Imagine if some awful group of people basically tried to do a kind of variation on a Smurf attack against Amazon, where they said, we're going to write a bunch of scripts, and they're all going to go to random pages on Amazon, and they're all going to fill up their cart with a bunch of items, and then move on to another item and fill those in their cart. And we'll have all these little bot programs that all have like millions of things in their cart, and then we're just never going to buy them. Okay? That would be effectively a massive denial of service attack. And if Amazon weren't prepared for something like that, it would totally ruin their day, right? So clearly, Amazon wants to limit how many things a single user could lock and how long they're going to stay locked, right? So last I checked, the limit was 100 different items within your cart. So they do put limits on that. And you have two more problems, deadlock and live lock. So what's deadlock in real life, right? In a non-technical sense. What do we say when, what do we mean when we say two wrestlers are deadlocked, or I'll accept that, but, well, a temporary tie, right? Nobody's making progress, right? They're kind of, if two wrestlers are in a deadlock, they're not just staring across from each other at opposite sides of the ring, right? They're like grappling each other, but they're both trying to like do something and the other guy's not moving, right? That's a deadlock. They're both pushing, but nothing's moving. So this can happen in databases too. So I'll give you an example. Everyone likes examples. Screen. Okay, so suppose you have a database with two records, we'll call U and V, okay? And one database update wants to update U, then V. and we'll call this update A. And we have another one, another B wants to update V, then U. And they start at the same time. What happens? Well, since we're talking about deadlock, you can probably guess that there's going to be a deadlock, right? Yeah. So A locks U and B locks V, right? Which means neither process can access its second row, its second record, right? A can't access V because V is locked. But what would be necessary to clear that lock is B finishing its own operation, which it can't do because U is locked by A. Okay, so this is a deadlock. Now, you might say, some of you might think, that's pretty unlikely, right? So what will happen in a deadlock is eventually the process will time out, okay? Eventually, processes will time out. And people won't be happy, but it'll be like the system is stuck for a while and then it'll eventually give up. You might say, yeah, it's pretty unlikely that you would have two database operations specifically try to access the same two rows like that. Yeah, fair enough. But in a very large system with chunks of very popular data and many requests at any given time, there's a pretty good chance that some of those operations will deadlock this way. Okay, and it might not be just with two operations, it might be with a whole cluster of operations that several of them all kind of overlap and are trying to access the same things in sequence, but A has to wait for B because B is waiting for D and D is waiting for F, but guess what? F is waiting for A, so ta-da, there you go. It's kind of a ring deadlock. And again, this can totally happen in a large database. Okay, so deadlock is a problem. You can have a similar problem called live lock. Live lock is where trying to resolve a deadlock actually perpetuates it, keeps it going. So real life example of live lock would be two people walking down a hallway, right? And it's a narrow hallway that just has room for one person. So suppose you're one of the person, you're walking on one of the people, you're walking on your right, the other person is walking towards you on their left. And about 3 feet apart, you realize that neither one of you has moved, and if you keep going, you're going to crunch into each other. So you could just start running straight at them and play the ultimate game of chicken, but most of us aren't going to do that, right? So what happens? What do you do as you get closer? What's that? You might step to the side, right? And bear in mind, this is a narrow hallway with only room for 2 people. But guess what happens? The second you step to the side, they're thinking the same thing, and they step to the side too. And where are you at? You're still both facing each other. So what do? You step back to the side you were on before, but the other person does the same thing, right? And then you have a little laugh about how ridiculous the world is, and then you figure out some way where you're going to get past each other. But we've all experienced this, right? It sometimes happens. Yeah. I mean, if not, then I got to tell you, you're kind of weird if this has ever happened to you. Anyway, but that's live lock. Live lock is you're responding to the deadlock, right? But the way that you're responding perpetuates it. So an example from our, A and B and U and V thing, live lock could be, suppose the system responds to this deadlock. It recognizes that a deadlock is there, but the way it responds is A and B attempt the same operation in reverse order, right? And then basically you have, since A is the opposite of, is the reverse of B and B is the reverse of A, what happens? There's still going to be deadlock, but it's going to be a different sequence. Or maybe both A and B recognize the deadlock has happened, so they both back off the process for like 2 seconds. But when they come back to try it again, since they rejoin at the exact same moment, boom, they find themselves in this exact same situation again, right? So again, deadlock and live lock, in a well-designed system, they shouldn't happen. But what do we know about systems? Not all systems are well designed, right? These are problems that have to be watched for. Okay, so just a couple more slides and then we'll call it a day here. So first, basic models, right? So some systems are going to have to deal more with concurrency than other systems. For example, if you're talking about banking, concurrency isn't a huge problem, right, in terms of performance. You have to be aware of it. Obviously, ATM problems, Bitcoin hack problems, you need to be aware. But the fact is, it's going to be pretty unusual for multiple users to try to access the same account data. And so it's okay to make people jump through some extra hoops to suffer some days for that to happen, right? That can be something like, oh yeah, it's unusual. You can say, for example, multiple people are accessing this account at the same time. Nobody can withdraw, nobody can make any transactions on it, right? Or you can be very careful and have some super governing process that says nobody can do anything until this governing process has approved that, there's nothing else going on with this account. So you can, again, make people jump through some more hoops. Retail, on the other hand, retail is a little different. Retail, simultaneous access to data is pretty much built into the model, right? If you're going through a grocery store and there's one last pineapple and you and somebody else reach for it at the same time, you're going to have to fight over it, right? That's only one of you's walking out with that pineapple. So you got to do whatever it takes. Anyway, but retail simultaneous access is pretty standard. It's something that businesses have to manage. Amazon can't, have a page that pops up and says, sorry, you cannot look at this item because someone else is looking at it. So they need some kind of mechanisms in place to prevent multiple people from overdrawing from inventory, but they also have to be much more cognizant of the, performance issues. All right, so talking about concurrency, concurrency is multiple users accessing the same data at the same time. Now, in principle, one of the things you could do is you could totally enforce isolation by saying our system is not going to permit any simultaneous access to any data. But in a lot of cases, that's really impractical, right? Because again, if these tables are large and queries involve entire tables or multiple tables, making everybody wait for everybody else in a large system, that's just not feasible. So no simultaneous access is one of those things that maybe sounds good, but you're not going to be able to make people happy with that. Another option is to allow people read-only access to the data. You can say, yeah, anybody can look at this, but we're not going to permit any changes to the data. So any number of people could look at a product page, but nobody can actually do anything to change that page while other people are looking for it. And again, that's not really feasible for Amazon either. For some organizations, some cases it might be. But Amazon wants people to be able to enter reviews at any time. If you're writing a review for a product, Amazon doesn't want you to have to wait for somebody else to finish writing their review. If you're trying to buy a product, Amazon, isn't going to say, sorry, somebody else is looking at this page. You can't buy a product, because that would necessitate, an update to their page. So they might adopt a model more like changes are permitted if there's more than one viewer, but have to somehow immediately be updated for all viewers, right? So again, if you go to Amazon and you buy a unit, whatever's on sale, they're going to decrement that count of how many are available, which is great, okay? But then that gets echoed, to a database that tracks how many there are. Anybody that's currently looking at that page, that information gets echoed to them within milliseconds to, update what they see. So, and for retail, that level of accuracy is totally fine, right? For Bitcoin, it might not be, because we talked about the Bitcoin hack. But for Amazon, the worst case is going to be, oh, I thought there was something in inventory. It got bought out. Life is hard, whatever. So the factors driving the policy choice for concurrency, number one, the number of users and the incidence of simultaneous access, right? The more users you have and the more prevalent simultaneous access is generally, you may need to allow some, right? So banking, you could be a very large banking operation, but still prohibit simultaneous access, and it probably wouldn't be much of a problem, right? It wouldn't be much of an imposition. If you're Amazon, you're a massive retailer, and you say none of that, forget it, it's just not going to work. Second, system complexity and likelihood of exploits, right? If your system is fairly complex, like one of these Bitcoin things, and perhaps the designers could have looked at each other and said, you know what, this is a complex system. We're not entirely sure. We think it's secure, of course, but we're not entirely sure it's secure because who knows? These security guys are, pretty good at what they do. Plus, it's a huge and juicy target, right? The ability to get millions of dollars worth of fairly anonymous cash equivalents, that's a huge target, right? For Amazon, somebody hacks Amazon and does that, maybe they order themselves a small truckload of books, right? Which would be unfortunate, but it's not the sort of thing that most criminals are really going for. So, yeah, again, likelihood of exploits. A Bitcoin hack is a huge and obvious target, and they should say, yeah, you know what, this is a big, complicated system, and we need to be super careful about concurrent access. And finally, importance of data integrity versus response time, right? So banking operation, data integrity is hugely important, right? You don't want somebody to do some instant wire transfer out of a bank for millions of dollars that then becomes untraceable and the money's just gone. Response time, this is why if you do a wire transfer, they generally give you a time the next day or a couple of days later where it's going to happen, right? They don't do instant cash transfers out of your account that way. Of course, you can do stuff like Zella. You can, send people money in short order. But if you're doing like a big wire transfer, like I forget why we did one. Oh, we did a refinance on our mortgage a few years ago, and I had to do a wire transfer for that. And, I scheduled it one day, and it was actually going to happen like a day or two down the road. Anyway, but like Amazon's, right, they want their web pages to load fast. They don't want it to all get slowed down because, the number of things in stock is a little bit off. That's, again, like Facebook with this eventual consistency. That's one of the things for Amazon. They're willing to cut corners and, have a little bit of delay of a few seconds maybe before these things get updated. It's not going to hurt anybody too much. All right. So that's all I got for today. Atomicity and isolation is where we'll start tomorrow. It's a little bit of recap there for Thursday. We'll come back Thursday and talk, and it'll be a hoot. Okay. Oh, last thing about the exam grades, don't panic, right? Remember what I said early on, that exam grades tend to be lower. You can still do reasonably well in the course, even if your exams aren't that hot. As long as you're like near the middle of the, near the average score, you're probably in the low B range, okay? So don't panic.